One of the central concepts in evolutionary theory is the idea of fitness. In a previous lecture, we kind of introduced this concept under the umbrella of a simple dynamical system, where essentially we consider the idea that fitness is related to how fast given species replicate. The faster you replicate, the higher the fitness. And we also connected that, along with competition, with mutation, right? The possibility that because random mutations take place in genomes, right, you can shift and become a different genotype. Well, more generally, beyond just replication, you can think in fitness in a much more broad sense. And I want to give you an example that is based on, not in biology, but in technology, right? Very simple example, and it will be very familiar to you. And will allow us to define a crucial concept here, the concept of fitness landscape, right? Imagine the following. You are familiar with the fork. You use it every day, right? We use a fork that has 4 teeth, all right? So I could say that an attribute of this system is this number, all right? And this is a familiar object that hasn't been there all the time. It was invented in Constantinople, and in the 11th century was adopted in France. Not this one. Before anything like this emerged, people used something like this, essentially a knife, to actually manipulate everything, right? The fork that was invented in Constantinople was similar in some sense, but it was just like this, right? Quite similar to the larger object that was used to pick meat, for example, all right? In France, it was adopted in the 11th century, and it wasn't, for example, in England until the 18th century. So it took really a while, right? And in the process, right, what happened is that this design evolved, right? You got more and more parts, right? From 2 to 3 to 4, not 5. You, of course, can imagine forks of any kind, right? And some artists have been thinking about, let's say, impossible forks, like fractal ones, anything you can have in mind, all right? Why not 5? Well, let's think about it. Imagine that I want to define some measure of how good is each design, right? How can I do it? Well, one way of doing that is to actually take a population of people, right? Like you guys, for example, and give you examples, samples of each design, right? And make a test, which will be you use the different designs for different kinds of food, right? You can take easily a piece of meat or something, some large object with any of them, right? But you will have a hard time to use these or these maybe for eating rice, for example, right? This is a nice design, and you could actually, every one of you could score how good is each design, right? You can think in a test where you give some score. What would be the outcome of that? Well, I need to put here 2 things. In this axis, it will be discrete number of things. I will put these numbers, right? It will be 1 to 4, right? The minimum, 2, 3, 4. And since I want to test about how good are designs, I would like also to think about possible designs, right? So I will also bring to you forks that are not there, right? With 5 or more, right? Okay? Kind of strange, I know. So let's put it 5. What is going to happen is the following. Of course, you go in this direction, and your scores are going to improve. Because you can use this for different tasks, right? It's a kind of flexible and much more useful instrument. But I could also use 5. Why not, right? But then it comes the idea of the cost, okay? Of course, I can generate this object or this object, but this is more costly. It might work as well as this one, right? But the cost is there. So if I put some score based on efficiency, how good is it to actually manage different kinds of food? And cost, right? What would be the outcome of this? Well, clearly, I will not be very happy, right? These are arbitrary units, right? Doesn't matter. I wouldn't be very happy with this, right? That is completely useless for rice, and I actually can damage myself by just putting it this way in my mouth, right? I will be more happy with this, because at least I can take a number of things. More happy with this, and probably quite happy with this, all right? Because it really works well. And maybe this could be similar, but thinking the cost, right? If the efficiency is similar, but the cost for whoever has to fabricate the object, it increases and quickly increases, right? This will be down, right? Let's put it here. And of course, for 6 or whatever, it will rapidly decay. This is a discrete system, but let me just draw the following thing, right? What I've just been showing you is an example of a fitness landscape, right? There's a landscape of possibilities, right? This is the number of tins of my fork, and this is a score that gives you how well it will work. But in terms of evolution, right? If you think in the evolution, the historical evolution and the selection that we impose by choosing different options, right? Here is the optimum, right? And what we should think is, whatever it happens in my system, right? Evolution should go into this direction, right? It's an abstract example, but you can easily manage to understand the intuition behind this. There's a process of variation, right? Inventors actually perform different designs, create different designs historically, right? Many times the same designs appear. We'll go to that in a seminar. And you can think in that in terms of this variability that you observe in nature, but you observe also in technology. But then there's the selection process, right? People uses the different designs, and selection pressures are crucial, right? Efficiency and cost are essential components of fitness. All right, I could expand that, but before I'll do it, when we think in this, right, we call, if there's only a single optimal solution, right, we call that a global optimum. Why? Because it's, the maximum fitness is there, it's well defined, and you get there from any direction, right? It's only one. You can think, now we'll make a kind of fun of that, in different attributes. We just thought about this, right? What about the number of tins here? But what about the length? Could be another attribute, right? If you want, then I can think in terms of the efficiency over cost, right? Related to two attributes. And now I'll need to plot a two-dimensional landscape. Let me just, this is of course just a qualitative picture, right? But it's easy to see. The shape will probably be different, right? But it's easy to see that for a system like this, where I have in one axis n, right? What I just saw before. And in the other axis, the length, let's say, total length or length of this, right? Whatever. If I measure again fitness, my efficiency over cost, right? Imagine that this here, right? This here is the standard length, right? The one that we use. I'm just mapping in this part this part of the curve, right? It will be a kind of a section here, right? But what happens if I move, if I, for example, increase the length? Here, I will have my fork, standard one, but strangely large, right? Not that nice to use, really. It's quite useless. On the other side, if I could draw it, could be the other example, right? Quite useless also, right? So fitness also the case in those directions. And you can feel the different possibilities here and clearly show that also in this context, right? When you have two attributes, so it's a two-dimensional fitness landscape, what I have again is a global maximum. All right? So that would be the conceptual framework. Okay. Unfortunately, well, so to speak, global maximum is a very peculiar case. It doesn't happen most of the time. The reason of that has to be found in one problem that we have when we try to optimize, right? And optimization is part of the engineering purposes that we want to design. What happens when I have two different components of the fitness that in a way constrain each other, right? For example, imagine that you want to, you have a car, an old car, and you have two choices. You have a given amount of money, so you have the cost there as a constraint, and you can do two things. Paint it from the outside, make it nice, although the engine is quite crummy, right? So you paint it and you're happy with your crummy car that looks nice from the outside. Or you cannot, you're not worried about how it looks from the outside, but you can repair the engine, right? You have to invest the money, right? Either in one thing or in the other, or you can actually reach a compromise. Maybe you can repair to some extent the engine and make it a bit nicer from the exterior. But that anyways implies that you have to make a decision that has to counterbalance the two parts of the story. So if I wanted to paint the landscape in that case, how it would look like, right? Let me just do an approximation of this, right? Here is how much I invest in painting, right? Here is how much I take care in repairing the engine, okay? And this is, right? What's the final outcome? Yeah, which can be measured in many ways, right? But just make an abstraction here. What was going to happen is that there's no such a single thing, a single peak here. What's going to happen is that I will have something that probably looks something like this. All right? That there's a kind of a space of possible good solutions, right? That are a compromise between the two of them, right? If I invest more in the engine, I have to invest less in painting, and the other way around, right? So the maximum here is not a single maximum. It's probably a whole range of values, right, that can be compared, okay? And more importantly and more generally, when you go into biology, there's no such a thing as usually, right, as a single peak, nor as a single simple fitness landscape. You have a multidimensional system. Let me illustrate that with an example that goes into biology again, to see why we need the fitness landscape and why the picture is not simple, right? And that, in fact, it's behind most of the big problems of doing a theory of biological complexity. Consider, for example, a cell, right? Okay? A cell in a very simplified picture again, right? You can think in the genome as a collection of genes, right? At some point we'll go into that. Genes talk to each other. It's not like separated entities. And you could, for example, have some genes that are involved in a way or another in growth. All right? But then there are other genes that are involved, for example, in maintaining genomic stability, right? So these are genes that if they mutate, right, what's going to happen is that the capacity of the cell for maintaining coherence, so to repair things when you replicate the genome, for example, is going down, right? Growth genes will be involved, for example, in diseases like cancer, right? And so on and so forth, right? Could be apoptosis, other things, right? And genes, whatever it is, right? This is from n plus 1 total number of genes, right? That are called housekeeping, right? Genes that are essential. Essential in what sense? That if they mutate, they are so crucial for maintaining cell stability or cell metabolism or whatever it is, right? If they mutate, the cell usually dies, right? So they cannot mutate. So as you can see here, I have a list, which is quite long, of genes that can have an impact on fitness, right? Whether or not they are mutated, it can have an important relevance to the likelihood that this cell, for example, replicates, right? If can replicate, of course. So if I want to build a fitness landscape with this, right, how can I do it? And what are the implications of this being a multidimensional system, right? Remember making a complete abstraction in the human genome, about 25,000 genes, right? In principle, that means thousands of dimensions, right? How could I make a mapping of that, right? Well, let's make a very simplified picture, okay? Where now my genome is a string of bits, right? Or a bit string, meaning that my genome could be represented as a collection of 0 or 1, right? Okay, there could be, for example, gene 1, and I can say it's going to be 0 if it's fine, it's no mutation, and 1 if it has a mutation. You see, it's a very simplified picture, and it's important to have that in mind because actually genes will be a first layer, a very coarse grain of description of a genome. And if I want to go into more finer details, I should go into the sequences. So in that respect, the space will be much larger, right? Because every gene involves thousands and thousands of nucleotides, right? So the same for this one. Okay, each one is a string of bits. So for example, right, my normal cell, so a normal cell would be a string of zeros, right? But you can see any mutation here involves having a 1, right? And it's a large space of possibilities, okay? It's actually 2 to the n possible strings, right? A number that grows quite fast as n grows, right? So how can I map this into some simple model that allows me to actually think about the problem and actually formulate theoretical models of that, right? And the simplest way of doing that is to use this Boolean picture, right? Where I have anything that I have in my system, my agent could be a genome, right? But could also be a sequence, right? And what I want to do is to have a formal way of mapping these, right? And use the idea of population and in the simplest way I can imagine to actually see how selection process takes place. The first step here is to actually define my space of genomes, right? So we do that by using the concept of a hypercube. A hypercube more strictly will be a Boolean hypercube, right? Consider the following. Suppose a very simple case where n is 3, very small, right? That would mean, for example, a system where individuals have a genome of only 3 genes, right? That, of course, seems ridiculous, but I can actually be interested in those 3 genes and the evolution of just those 3 genes. So that's something I can use, right? In that case, my space of the possible, right, will go into strings, right? Imagine that this is SK means the genome, right, the digital genome of the kth individual, right? I will have 3 components, all right? Each one can be a 0 or a 1, right? Boolean description. This can be extended into the 4 letters alphabet, for example, if I'm talking about sequences, but it doesn't really matter, right? My space of the possible genomes would be a cube, like this. All right? All right, where do I place each string? From 0, 0, 0 to 1, 1, 1, okay? And the standard is I put the zeros here, okay? And we will play with a space where the neighbors of each string will be single mutant networks, single mutant sequences. So I mutate, for example, I change the last bit, have this. I have the middle bit, have this, I have the first bit, right, for example, okay? It's arbitrary if I choose this in this way, doesn't matter. The important thing is that I maintain the consistency. If I mutate from here to here, right, consistent with these two, right, I can go here by mutating any of this or this, right, the first or the second. Same here. Right? Just need to see who is here. And same here, right? The single bit mutations. And here will be this. So I have my 2 to the n, 8 possibilities, right? This just defines the possibilities of genomes. Doesn't tell anything about how can I move in this space, where can I put the population, right? And more importantly, where is the fitness here? I need to define the fitness, right? Let's start from this. This is just the topology of my cube. Why we say hypercube, right? I'll go through that in a moment. I could consider 2 simpler examples, right? This is already simple, but I could also go. This is usually called as the H3 hypercube, right? I could go into more simple cases that we will consider, right? In our examples, mathematical examples, we'll go into those simple examples. Just 2 bits, those will be n equals 2. It's easy to see that in this case, that's the way I can organize my single mutant elements. That would be my H2 space, all right? And I can go even to a lower scale, right? And that is fine if I consider, for example, a single gene with 2 alleles, for example, right? Or having or not a mutation in a given element in my sequences, 0, 1, right? That's the simplest, of course, I can define. But I could go up in this dimensionality. What about the 4-dimensional hypercube, right? It seems that I cannot actually write down that, but I can, right? 4 dimensions. Let's go for that. I can do it using a little trick, right? Let me put here a large cube. All right, that could be my 0, 0, 0, 0. I'm going for the 4-dimensional, right? We have here 0, 0, 0, 1, etc., right? But how can I deal with that? Well, let's put a smaller cube inside. Let me see if it's possible to make it as nice as possible. I put another cube inside here, right? And now I make these following connections. I connect this with this, this with this, this with that, etc., etc. Okay? All right. There's a whole mathematical literature about these hypercubes, right? And it's real fun. Actually, it's here. And you can check that now the 1, 1, 1 is here, right? And distribute the rest, okay? Of course, going into the 5-dimensional case could be a bit more difficult. You can do it actually in the following way. I could go from this to 4 dimensions by taking this cube, shifting, right? In a way, it's exactly this, right? I'm shifting and creating another cube and connecting the vertices. But of course, it's becoming more and more cumbersome, right? Very good. So this is the first part. Now we have a space of possible genomes, right? Digital genomes, very simplified. Now the question is, how can I introduce in this topological space fitness? Now we have defined our space of possible genomes, right? The digital genomes and an oversimplification of the real thing. But nevertheless, as you will see, it's a really powerful way of exploring the space of states of a system, right? Using something that is, in a way, Darwinian selection, right? This is our space of variation, the repertoire of possibilities that you can have there. What is missing there, right, is the two things. One is that, of course, these are strings of bits. Remember, this is our collection from 000 to 111 of the possible digital genomes. We need a population, right? A population is necessary. We need real agents that carry the genomes. And more importantly, we need fitness. We need to define somehow who is better in terms of replicating itself, right? Because that we know is basic ingredients of Darwinian selection, and the picture that we will use here is precisely kind of the Darwinian image of evolution, something that takes place slowly and continuously, all right? We'll discuss these and extensions later on. Okay, let's think right now in terms of just mathematics, not in what's the exact meaning of our fitness function. Just define f, right? That could be rate of replication or any other attribute, right? Remember the example of the cancer cells. I can be better, maybe not because I replicate faster, but maybe because I'm more able of not dying, okay? So different things that can be part of the fitness. But let me give you an example, first of all, right? Let's invent a fitness function. Suppose that for whatever reason it is there, right? The fitness of an arbitrary string in my system, right, is just the fraction of ones, that I have, right? So in this particular case, since I only have 3 elements, what I do is just to make the sum of bits, right? The more ones I have, the higher is the fitness, all right? For example, these ones could be some components of growth. The more genes are mutated that make grow faster, right, the better, okay? Well, if I use that and I map that into my hypercube, right, what can I write here that helps me to can guide a little bit? Well, if I just take into account this simple example, right, and now I assign to every vertex a little circle that somehow weights the fitness, what I will have is here is the highest one, right? For example, the best replicator. The neighbors having only 2 ones, right? Those here have a smaller fitness, okay? And then the 2-bit mutants from here, right? Here, here, and here, and you can see there, just single mutations in the ones, right? Have still lower fitness, and here will be the minimum one, right? Could be 0, or we can add. I can add to this some minimal value if it's replication, for example. Otherwise, it would be dead, right? So from this scheme, I can say something already. If selection proceeds in a way that improves fitness, meaning that I have a population of individuals described by whatever attributes mean 0 and 1, right? And every time I have a reproduction event, a mutation can happen. Those mutations that favor increasing the number of ones will be selected. So the flow of change in terms of the selection process has to go in this way, right? Improvements in the number of ones push me into these vertices here, and this keeps going as I accumulate ones in my system. So I should expect something like this to happen, right? That selection pushes the system into here. This particular case, this is one example of one fitness landscape in my discrete space, right? Will correspond to the single peak landscape that I just discussed on the fork example, right? In the fork example, I had this single maximum, all right? And in a way, this is exactly the mapping I have here. Anything flows into just most favored state, right? So that's an example of a fitness landscape in this binary world, okay? I could define others, all right? For example, I could define an example where, let's consider the simplest cases, right? One simple landscape also could be something like everything is exactly the same, all right? So it will be a neutral landscape. Neutral landscape means that the fitness is identical, it's no difference, right? It might seem a boring thing. And it means that actually if I accept neutral changes, right, flows that do not change the fitness, I could have things that go into any direction. All right? So I will actually move randomly around the hypercube, right? It might seem a boring example. It's much more relevant than you might think, right? Neutrality helps exploring. Another example, right? You can think about how you actually write down mathematically this, right? Is a state, so a fitness landscape where, for example, you have these two maxima, right? Whereas the rest, for example, go like this, right? So flows take place in these directions, right? That would correspond to an interesting example where in my simple picture of mountains, right? In an idealization would be kind of two peaks, right? So it's an interesting example because that connects with an important message from Darwin's theory of evolution, right? Kind of this extremely simplified picture of what Darwin actually envisaged, that evolution implies that there's a tree of life, right? That we are connected with everything that happened in evolution, right? Forming a tree. A tree with many branches that go nowhere, lots of extinctions, right? Actually, it is estimated that probably 99% of species that existed in our biosphere sometime are extinct, right? Or, as a mathematician said, in kind of a funny way, on the first approximation, everything is extinct, right? So this is a tree of life, right? And I want to point that this is an important result. First, I want you to think about how does this map into this, right? But when we define the dynamics of this, you'll clearly see how it works, right? But there's an important message that I think is good to mention. We know that evolution happened, no matter what creationists say. It happened, and in the times of Darwin, most of the evidence came from two sources. One is the fossil record, right? We go down in time as we see the record that is stored in the strata, and it was inferred from that a lot of this tree. But even if fossils did not exist, right, the fact that we have genomes, and we'll see a mathematical model that shows how to calculate the times for divergence, right, we could say that evolution happened, right? Evolution is a fact. Sometimes creationists say it's just a theory, as it is gravitation, for example. Yes. So there will be more landscape that you can actually imagine, right? We are in the very low dimensional case. The last thing that is missing here is dynamics, right? Okay, I can define that. How can I define the final part of the story? A population dynamics of actual agents carrying genomes that move in the fitness landscape. And to do that, we can do that in many ways. And one of the simplest ways of doing that, right, is what's called adaptive walks, right? Adaptive walks were invented by Stuart Kauffman as a simple way of actually thinking and exploring evolution, right, in this particular context. How do they work, right? And I'll give you an algorithmic description, all right? Well, the first thing is I have my setting, right? Let's suppose that genomes have a given dimensionality, right? More importantly, right, suppose that I have my genome size. I use this notation, which is quite standard, nu, the Greek letter. They have a population. Well, populations are important. Small populations, large populations, they have an impact on evolutionary dynamics, all right? And then I have a fitness measure, all right? Important to say, we will assume that this fitness exists and is associated in a well-defined way for any genome I can think. We might know the fitness as it's here because I define mathematically in a way how the fitness is, but in general, we will not know what this exact fitness will not know, right? So this is something that when I have my agents moving in the landscape, they will find out, right? But anyway, the thing is the following. this is what I can use, the basic thing. We start with a population, right? That's my setting. That starts from a given vertex of my hypercube, right? For example, my population starts here. I draw this large circle, which is everyone is there. Everyone is 0, 0, 0 genomes, right? In general, whatever genome I've chosen, all right? It doesn't need to be the case. I might just put all kinds of strings there, but just to start with thinking about that, imagine that they start somewhere, right? Everyone is here. Now, if you want to make the mapping with things that we haven't observed before, we still are in this picture of a well-mixed population, right? But now my agents, right, are strings. So if you want, here, what I have is this, all right? Strings of bits, right? Very good. What I'm going to do is the following. I'll consider a number of generations. So I want to make the system explore the hypercube and trying to find out Higgett fitness values, right, over t generations. I'll let you know what is that. In each generation, what I'm going to do is take every single agent, right, genome if you want, and perform this following rule. If I take this genome, with some probability, I make one mutation, and just one, okay? I will check, a mutation means what? Mutation means, for example, if I'm here, 0, 0, 0, imagine I mutate the third bit, right? Means that I'm going here. And what I'm going to do is look at the fitness here, and if it's higher or equal to this one, the original one, I move, because there is an improvement, or maybe it's nothing, but it's not no less fitness, right? And I call this an adaptive walk, right? I walk in the hypercube to one of the neighbor single mutant vertices, all right? And that's essentially all, right? Once this is completed, right, I go into the next generation, which means repeat that, right? And in such a way, as you can already have in mind, what I'm going to do is to allow my genomes to actually diffuse in this space, right? Until what? Well, if the rule is I can move into a different vertex by mutation if fitness increases, that will stop when fitness is not increasing anymore, right? Or when the number of generations that I put as a maximum, right, is achieved, right? Let's write down this in terms of an algorithm, right, a flow diagram. And we can do this in the following way. We start with this counter. It's going to count the number of generations, all right? Now, I increase this, sorry, this is t, excuse me, right? T small. If, oops, sorry. I ask myself, of course, if I have completed my set of tries, if the number of generations is already achieved, I stop. All right? If not, I have to start applying my algorithm. All right? Okay, I have to follow the whole collection, right? I forget, I also here have set k equals 0. I have to look at every single element in my system, right? So I take k, all right? This is my counter to see which agent or digital genome I have to choose, right? And again here, since I have a finite number of elements, right? Once this is n, okay, I just have to go for the next generation because I look at all the possible genomes, all right? So if this is n, okay, if this is n, I just need to go back here to the next generation, all right? Okay, now the most important thing, this is just a counter to see if the algorithm is finishing or not. Now, if this is yes, right, next generation, if it's no, now I have to look at my agent, my genome, right? Choose one particular gene at random. Gene means bit, okay? And decide if I make a mutation or not. So, I choose. Let's write down this here. For each of these Ks, right, I have my individual, which is string. In general, right, with new bits, right? Do not lose our intuition, thinking the three-dimensional. Like for example, 010, 011, whatever it is, all right? So I choose one of these bits at random. Let's say Ki, right? And generate a random number. Okay, this is a random number. Random number between 0 and 1. Why is that? Because I want also to use something that I forgot to mention, a mutation rate, right? Mutations need to happen with some probability. Sometimes in this algorithm, this is just taken 1. Yeah, I'll always do that, right? But let's make it more general, right? So now I'm almost there, okay? SKI will go into 1 minus SKI, which is a sophisticated way of saying 0 goes to 1 or 1 goes to 0, right? With probability mu, right? How can I do that? Sorry, it's a bit non-standard, this. This is going to happen if the random number I generated is less than mu, which is in a way, one way to say that with probability mu, I perform this change, all right? Now, I have my string. I have made one mutation, okay? The question is the fitness of the new string larger or smaller than the one I had, right? That's what I have to ask, okay? This goes now into the question of, is f of sk prima larger than f, sorry, of sk? So in other words, is my fitness improving, right? Or, since I can also define that, or at least it's the same, right? I gave the possibility here, right? That defines the selection process. I can go up or down, right? And I almost there. If no, right? I just need to go into the next K, right? I don't do anything, right? I don't do anything. I just go into the next agent and try again, right? If it is, right? Yes. What I do is to replace the string that I had at the beginning by the mutant, right? So sk is my sk prima. Just to make sure, sk prima means the same I had here, except that the ith bit has been changed. All right, my bit here has been replaced by the opposite one. All right, I do that, and again also go here. Right? Okay, that's essentially what means to perform an adaptive walk. Right? Let's rapidly summarize that. I have a population of agents, right? In my simple cube here, for example, means that I start somewhere. Again, now if we're doing that, everyone is here, right? 0, 0, 0 for everyone. Imagine that my landscape is that single peak one, the number of ones, right? I will go here for every single element. I look at what happens when I shift one bit. It might be the first or the last or the middle, right? But any of them, it's fine. And with some probability, right, I'm going to start moving the population to the nearest neighbors, right? I'm starting to diffuse uphill, right, because the fitness grows. When I finish with all the population, start again with everyone, everywhere, right? And I repeat the same process. At every step, with probability mu, I'm going to see that the population is moving, right, to where? They will keep moving. Is natural selection happening until everyone is there, right, in the top hill. And for this particular situation, nobody is going to be anywhere else, right? Everybody flows into the single peak, okay? All right. Is evolution an algorithm? That's something that I want you to think about. To what extent I can do this comparison, right? The good thing for us is that in terms of design, right, evolutionary dynamics, as I just defined, is a way for engineers to actually find out solutions to really difficult problems when there's a large repertoire of possibilities, and sometimes we don't know what's the best solution. And more interesting, as we will see, sometimes this kind of dynamical process allows actually to find out solutions that we cannot imagine.